reaction order is second order. Right? Section 11.6, the collision model. So this is built around the central idea that molecules must collide in order to react. I mean, and I am somewhat amused that this is still a controversial to a very few number of people who do not think that this is what happens. But I mean, like, how else are you going to get reactions to happen, right? Those molecules need to be in contact with other molecules in order for things to happen. But it's going to postulate that the energy to break bonds comes from the kinetic energies possessed by the reacting molecules before the collision. This kinetic energy is changed into potential energy as the molecules are distorted during the collision to break bonds and rearrange atoms into the product molecules. So you're going to break some bonds, you're going to form some bonds. If I take my Civic and I run it into a haystack, I'm probably going to get Civic parts in the haystack and haystack parts in my Civic. Meh. All right, so our collision model is going to have one of these activation energies that must be overcome in order to produce a chemical reaction. It's related to the bond energy and can sometimes be used in supporting one mechanism over another. Right, so where is this energy coming from? Well, in order for me to undergo a reaction, I got to break some bonds. I got to make some new bonds, right? The first step is I got to break the bonds. And that's usually going to take some energy. The higher the activation energy, the slower the reaction is at a given temperature. So if you remember our Boltzmann distribution for molecules, right, a slow, cold molecule is going to have very few that are over the particular energy threshold, and something that is hot is going to skew this over to the right a little bit, and so now more of them will be able to overcome that activation energy. More of them have sufficient energy. Those should be in the same spot. There you go. Our activated complex or transition state is an arrangement of atoms, and it's usually going to be drawn up at the top. So a change in potential energy is a function of reaction progress for this reaction between bromonite and decomposing into NO2 and Br2. And we start off with our reactant, right? We're going to form our products. There is an energy difference, a delta E or a delta H that is associated with that, and that's usually going to be in joules or kilojoules, right? And that's going to be our delta H, a reaction to tie that in. We're going to have an activation energy that we need to overcome. So in order for us to make our products, we're going to need to make this intermediate. So we're going to take our BR-NO molecules and we're going to form this transition state up here at the top that they've drawn, where we're starting to break this bond here between the nitrogen and the bromine. And we're starting to form a bond between the two bromine molecules. So the bromines are leaving the nitrogens, they're finding another bromine, I'm breaking some bonds, that's going to take energy. The activation energy, EA, represents the energy needed to disrupt that molecule so that they can form products. The quantity of energy represents the net change in energy going from reactants to products. Right? And so we've got our reactants over here. They're going to form this transition state where some bonds are breaking and they're starting to form other bonds. And we're going to form some products over at the other end, and they're going to have a net lower energy. If they have a net lower energy, this is exothermic. What happens if they end up with a net higher energy? Right? If our change in energy, our delta H, is a positive number, well, it's endothermic. Right? Heat being produced or heat being consumed. So only collisions with energy greater than the activation energy are going to be able to react. The fraction of effective collisions is going to increase exponentially with temperature. So the number of collisions with the right energy is going to be equal to the total number of collisions times EA to the RT. And you're going to see this fellow quite a lot, where EA is the activation energy, R is the universal gas constant in 8.314 terms. T is the temperature in Kelvin. And E, our natural log E, to the EA over RT represents the fraction of collisions with enough energy or greater at a given temperature. All right, so as our temperature increases, as we go from T1 to T2, where T2 is higher, more of those molecules are going to have sufficient energy. Our cold one has a limited amount. Our hotter one has far more that reach this EA barrier that are going to have enough energy to overcome this activation barrier. All right. So you can think of this as, here is that same plot from before. Here's our two Boltzmann-like distributions. Right, our cold one only has a small fraction. Our hotter one is going to have a larger number that are above the threshold to reach that activated complex. If we get moreover this pump, more things are going to happen. I've got a faster rate. Right, so this is why K is going to be proportional to our temperature, because our temperature is proportional to our energy. And if our energy goes up, more of those things will be able to overcome our activation barrier, the more product we're able to make. And this one right here, where our product is at higher energy than our reactant, right? This guy's endothermic, delta H. This is a positive number. All right, so our collision has to have enough energy. That's requirement number one. Right? Got to have enough energy to make it up over the hump. Collision energy has to equal or exceed the activation energy. The relative orientation of the reactants must allow for formation of any new bonds necessary to produce the products. So if you take two Legos, right? Here's my Legos. Right? And I take my Lego brick and I've got the bumps on one side. Right? And I'm like, I'm going to Lego. And I try to take it with another Lego brick with the bumps on the front side, and I try to put these together, am I going to Lego? No, I'm not going to Lego. They have to be in the right orientation. So I've got to have the bumps matching up to the holes. Can't do bumps to bumps, can't do holes to holes. Got to be in the right orientation. So the relative orientation of the reactants must allow for the formation of any new bonds necessary to produce the products. So considering these requirements, the rate constant can be represented as follows. So K is going to be equal to Z times P times EA to the RT. Right? So this is going to show us how kinetics and rates tie into energy. Because remember, this class is all about the energy. Right. For most reactions, for a reaction to take place, the reacting molecules must collide with each other. On average, that happens about 10 to the 9th collisions per second. Once molecules do collide, they can react together or they may not, depending on two factors. Do they have enough energy to break the bonds holding the reactant molecules together, and whether or not the molecules collide in the proper orientation for new bonds to form. So for a collision to lead to overcoming the energy barrier, you got to have enough energy. Right, so if you got Lego 1 and you got Lego 2 and they're in the right orientation, but you're just like, I can't push them together because I'm not strong enough, you're not going to be able to get those two Legos together. So you got to have enough energy. They also have to have, so they're energetic collision, that's going to lead to a reaction. But these guys that are in the wrong orientation or don't have enough energy will not. The collision frequency is the number of collisions that happen per second. The more collisions there are per second, the more collisions can be effective and lead to increased product formation. So if I've got more collisions, right? If I've got more molecules, if I increase the number of molecules, my chances of having a collision, my probability, is going to go up, right? So if my concentration goes up, my number of molecules goes up and my probability goes up. So this is our tie to why is our rate going to be equal to K times the concentration of A. Well, because I got more A, I got more things that are around to collide with each other. The higher the frequency of collisions, the faster the rate. Collisions in which these two conditions are met and therefore lead to a reaction are called effective collisions. When two molecules have an effective collision, a temporary high energy and unstable chemical species is formed. We call that the activated complex. Proper orientation results when the atoms are aligned in such a way that the old bonds can break and the new bonds can form. The more complex the reactant molecules, the less frequently they will collide with the proper orientation. So if you got some honking big complicated molecule, right, it's only going to react in one spot, it's less likely to happen. Reactions in which symmetry results in multiple orientations, leading to a reaction to have a probability P slightly less than 1. For most reactions, the orientation factor is less than 1. So here we've got a reaction between two NOCl molecules. Right? I need to form NO and Cl2. Depending on how I choose to bring those things together, right, I'm going to end up with an ineffective collision, right? If I try to match the nitrogen into the oxygen into the oxygen, right, I'm not going to form NO, right, or a Cl. If I try to bump the Cl into the oxygen, it's not going to happen. But if I try to put the chlorines together, well, that could be an effective collision because they're in the right orientation for these chlorines to get together. Right? And when they do that, you're going to be left over with some NO molecules. So they got to be in the right orientation. So let's look at this equation. K is equal to ZPE to the EA over RT. Right? Z is our collision frequency. So how often do they bump together? P is what's called a steric factor, and it's always going to be less than 1, which reflects the fraction of collisions with effective orientation. So how many do we have? The number do we have, right? So if you throw out 10,000 passes, right, you're going to get more completions than if you just throw out 2, right? P is the right orientation, right? So you have to get your receiver in the right direction, right? If he's facing the wrong way and it bounces off of his helmet, it's not going to be effective. EA is the activation energy. Do you have enough energy to get up over that activation barrier? Right? If you're thinking football, can you throw that Hail Mary pass that you're trying to throw, or do you only have 10 yards of range? You got to have enough energy to make it up over that hump. Our rate constant can also be rewritten in the form of what's called the Arrhenius equation. Right? So we're going to take this, ZPEA to the EART, and we're going to combine our Z and P into a new factor A, which is our Arrhenius constant. It's going to roll together our steric factor and our collision frequency, and we're going to get K is equal to A, our Arrhenius factor, times E to the EA, our activation energy, over RT. So A is our frequency factor. Frequency is just how many and are they in the right position. So A just decomposes into Z and P. Our Arrhenius equation is we're going to take the natural log of each side of the Arrhenius equation. So our Arrhenius equation said, we're going to rearrange this so we get natural log of K. Because if we plot this guy out, we can do a plot of temperature on X and K on Y. And when we do that, we're going to end up with K goes up over time in some sort of nonlinear way. But we want to make this a nice linear equation. And where have we seen this problem before? Right? It looks a lot like that Clausius-Clapeyron equation, doesn't it? We're going to do 1 over T and a natural log, not of pressure, but here of K. So we have the natural log of K is EA over R times 1 over T plus the natural log of A. As a reminder, our Clausius-Clapeyron was natural log of pressure is equal to minus delta H over R times 1 over T plus the natural log of our initial pressure, right? So very, very similar equation. Our slope is going to be EA over R, so we can get that activation energy out. So you can do a series of experiments at different temperatures. I run the same experiment under different conditions. I get different rates. I calculate a new K. I plot up new values of K as a function of temperature. Do my math magic to transform that into a nice straight line. And I can find out what that activation energy is. So this is part of why kinetics and rates of reaction are so important to us as chemists, is that it's going to give us information about how big that activation energy barrier is, which is going to tell us about, well, what is the potential structure of that intermediate. So for a reaction where the rate constant obeys the Arrhenius equation, a plot of natural log of K versus 1 over T is going to give us a straight line. All right, so we can graphically determine that activation energy. We'll do 1 over K, T on X in Kelvin, and our natural log of K on Y. Our intercept, that's going to give us our A term, which remember is equal to our number of collisions times the orientation, P times Z. Our slope is going to be EA over R, where EA, that's going to be our activation energy. Got our products and our reactants. That's our natural log of K versus 1 over T, where our slope is EA over R, and our intercept is the natural log of A. And so just matching up with this Arrhenius equation here. All right, so here's an example where we determine that. We got a series of reactions. It's going to be studied at several different temperatures. So this is our independent variable, right? And our K is going to be our dependent variable. All right, so we've measured K at a series of different temperatures, 20, 30, 40, 50, 60 degrees, right? We're going to need to right away convert that into Kelvin. We're going to take this K value and we're going to convert that into a natural log. So we're going to take our data in C, convert it to temperature. In Kelvin, convert that to 1 over T. That's going to be our X. We're going to take our K values, which we would have gotten from, rate is equal to K times A to the 1, B to the 1, right? Whatever we get as our K constant. Convert that to natural log of K. We're going to plot this guy and this guy. Plot that natural log of K versus 1 over T. Our slope is going to be change in slope over change in 1 over T. So 1 over rise over run. We're going to end up with our slope being EA over R. So change in natural log of K from two positions, say here and here, and our change in 1 over T, delta X, delta Y. Right. Our slope is EA over R. We said that our slope is going to be E over R. We're going to rearrange, pull EA out on one side. So we're going to take our R times the slope. So 8.314 joules per mole Kelvin times minus 1.2 times 10 to the 4th Kelvin. It's going to give us 1 times 10 to the 5 joules per mole. Thus the activation energy is going to be 1.0 times 10 to the 5 joules per mole, or 100 kilojoules per mole. And that's a pretty typical value for an activation energy. The values of K1 and K2 can be measured at temperatures T1 and T2. So this is going to give us two different things to put into our Arrhenius equation. Right? So now we've got 1 point and another point, and we've got our slope like that. Right? We know where B is over here. Right? That's going to be our Arrhenius constant. Our slope is going to be B equal to the natural log of our Arrhenius constant, our slope, M will be EA over R. So we've got 2 different points. I can do a 2-point formula just like we did for Clausius-Clapeyron, right? Here's a 2-point version of our Arrhenius equation. We got natural log of K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2. And that's really, really similar to our one of the versions of our Clausius-Clapeyron, where's the natural log of P2 over P1 is equal to delta H over R times 1 over T1 minus 1 over T2. Could you rearrange this and do one of 4 different versions for this? Sure, yeah, you could do ln of K2 over K1 is equal to minus EA over R times 1 over T2 minus 1 over T1. Right? Just like you could do a different version of Clausius-Clapeyron. So let's continue with determining our activation energy. The gas phase reaction between methane and diatomic sulfur is given by this reaction where we've got CH4 in the gas phase and sulfur, 2 sulfurs also in the gas phase, to give us carbon disulfide and 2 hydrogen dihydrogen sulfides. At 550 degrees C, the rate constant for this reaction is 1.1 liters per mole seconds. And at 625 degrees C, the rate constant is going to be 6.4 liters per mole seconds. We're going to try to find EA. So just like you would have found delta H in your Clausius-Clapeyron equation, here we're going to find EA from our Arrhenius equation. So our data is shown in the following table where we've got our K values and our temperatures. Want to convert those to Kelvin right away. We're going to do the natural log of K2 over K1. And then we're going to do is equal to EA over R and 1 over T1 minus 1 over T2. We have a T2, we got a T1, we got a K1, we got a K2. All right, we're going to solve for EA. So we got the natural log of 6.4 over 1.1 is equal to EA over 8.314 joules per mole Kelvin times 1 over 823 Kelvin minus 1 over 898 Kelvin. So we'll rearrange that to solve for EA. So we'll do R times the natural log of 6.4 over 1.1 divided by 1 over T1 minus 1 over T2. And when our joules cancel, our joules won't cancel out, but our kelvins will cancel out. And this guy is unitless. We're going to end up with joules per mole, 4.1 times 10 to the 5th joules, or 140 kilojoules. All right, pretty straightforward. Math is going to be the same as you would have seen for Clausius-Clapeyron back in chapter 9.